next thing that we're going to learn about in our study of polynomials is dividing. Now, before we actually divide a polynomial, just let me refresh your memory on long division. So with long division, we're trying to see how many 21s go into 67. And the most I can get in there is 3. Then I multiply these, so 3 times 2 and 3 times 3, and I subtract. So when I subtract these, and I bring down my other placeholder, now I'm trying to see how many 21s go into 42, and I can fit 2 of them, and when I subtract, I have no remainder. So this is a long division that has no remainder. What we're going to try to do is we're going to try to take that same concept, but we're going to apply it to a polynomial. So I'm trying to make this 2x, see how many 2x's go into 6x squared. And I can actually fit 3 and x. Because when I take 3x times 2x, I get 6x squared. And 3x times 1x, that's a 3x. And just like long division over there, I subtract. Now when I subtract, that goes away. I get a 4x, and I bring down my next placeholder. So now I'm trying to see how many 2x's go into 4x, and it's 2. So when I multiply 2 times 2x, I get 4x, and 2 times positive 1 is a positive 2, and when I subtract on this one, I get a remainder. And sometimes we left the remainder down here. Sometimes we would put our remainder up there. So long division has the same kind of process, whether it's numeric or it's algebraic. But both of these fall into kind of this algorithm. We have some polynomial. We want to divide out our divisor, come up with some kind of answer here, and we may have a remainder when we're done. Now, the application of this that we want to try to get to, we're going to teach you how to do this division, but the application comes in this statement right here. If the remainder turns out to be 0, like it did here, not necessarily like it was here. So, if the remainder is 0, then what we divided by and what we got for an answer are considered factors of that polynomial. So I'll say that again. Q and D, the things that sit outside the divisor bar and above it, are factors of P if we don't get a remainder. That's going to become important when we start applying this. But our goal today is to learn how to do some of this polynomial division. Now there's 2 ways of tackling it. The first way we're going to talk about is long division. It's what I demonstrated in my first example, and I've got this one already set up. So here's my polynomial, here's what I'm dividing by. And my goal is to make the first piece of each of these look the same. This is missing a 4 and an x. So that way when I multiply 4x and x, I get 4x squared. But I'm also going to multiply the 5 before I do my subtraction. Now, if I did this right, the x squareds go away. I'm going to subtract here and bring down my next placeholder. So now I'm doing the same thing. I'm trying to make these look the same. And this looks like it's missing a 3. So I'm going to multiply a 3 in here and here before I do my subtraction. Now, this goes away. Perfect. This is what we're trying to examine. I ended up with a remainder on this one. If you get a remainder, according to this little theorem down here, these are not factors of that polynomial. Because if I have a remainder, they just aren't. If this remainder was 0, I'd have something to work with. Now there's a couple ways to write remainder. We can do it the old school way and say a remainder of negative 31. But sometimes you'll see it written like this. They'll take that remainder and they'll write it with the piece that we divided by and just tack it on to the end. I'm okay either way. If you just want to say a remainder, or if you want to put it back over what you divided by, they're both acceptable. Now, they'll disguise this division. They'll throw it at you as a fraction. This is the same type of problem. They want you to take this top polynomial and they want you to divide by x minus 7. I didn't leave myself much room. I'm trying to make those look the same. This is missing a 3 and an x, because 3x times x would be 3x squared. 3x times negative 7 is negative 21x. So my first step, once I've established what I'm going to put here, is I multiply. And then my next step is to subtract. 3x squared minus 3x squared goes away. Negative 29x minus a negative 21, that means add. And I bring down my placeholder. I go back to that multiplication step. This is missing a negative 8. Negative 8 times x, and negative 8 times negative 7. So I multiplied, then I subtract. And this one shapes up really well. There's no remainder. That's important because this polynomial has 3x minus 8 and x minus 7 as factors. So for those of us who struggle with factoring, if I'm trying to find factors of these and I think this is one of them, I now have both of them. So I can say 3x squared minus 29x plus 56 factors into an x minus 7 and a 3x minus 8. So maybe that'll help some of us with our factoring woes. Now, they will also disguise them like this. Is x squared plus 1 a factor of 3x to the fourth minus 4x cubed plus 12x squared plus 5? Now, there's something important that shows up in this particular problem. When we do long division, even with the numbers, we never left any spaces. We never left anything blank. There was always a hundreds, a tens, and a ones. There's a squared, a linear, and a constant. This is missing one. So when we go to divide this, we're going to put in that linear term. We have to have that placeholder. And to make it even more complicated, x squared plus 1 is also missing something. That linear term. We have to put in those placeholders. We have to put it into standard form for polynomials, largest power down to smallest power with everybody accounted for. Once we've done that, it's just long division. We're making the first terms look the same. I need a 3, and I need an x squared. Multiply. And then subtract. If I did it right, the first term should definitely go away. And bring down your placeholder. Now I need to multiply. This needs a negative 4, and it's short one of the x's. So I'm multiplying here. And then I'm going to subtract. And believe it or not, most of the mistakes are made adding and subtracting. Doesn't matter if this is positive or negative, it's 0. So 9x squared minus 0x squared. Here I have a minus negative, and I bring down my last placeholder. Now I can still do one more round. I'm still dealing with x squared. I'm short a 9. subtract, my squared goes away, but I did not get rid of everything. I have a remainder, and there's no more division that I can do because I can't make x squared look like this. If you look at the top, I got down to the constant already. There's no more division. I definitely have a remainder on this one. You can leave it here. You can write it at the top. You can even put it as 4x minus 4 over x squared plus 1 if you want to. That would be the proper polynomial notation. I'm fine with you putting a remainder. This one looks super simple. And there may even be a few of you who are just going to cross out x's and cross out 2's, but that's not what they're asking here. If I put in all my placeholders, x to the 5th, x to the 4th, x cubed, x squared, linear, then the constant, this is actually a really long problem. And I'm pretty sure I didn't leave myself enough room. We're dividing by x minus 2. I need a 2x cubed and I would continue this process to see if this works out. I will let you in on a little secret. This does work out, so I will leave this one for you to try on your own. Now, there is another way that we can do polynomial division. That's what we're going to take a look at next. Synthetic division is another way of dividing polynomials, but it's done very differently. The two key pieces here are we're going to look at coefficients only, and the x minus a, we're going to actually take the a out of the parentheses and use just the a. So let me show you an example. This says, is x plus 2 a factor of this particular polynomial? I'm going to start with this polynomial, and I'm going to take out just the coefficients. So we have a cubic, so I actually have 4 pieces here. And x plus 2, they're trying to find out if x plus 2 is a factor. So when we take that out, we're actually getting a negative 2. Notice in here it was negative, we took it out, it was positive. If it's positive, when we take it out, it's negative. So now, we're already set up to do synthetic division. Now we always bring the first one down. That one doesn't change. And we're still going to do multiplication. So we're going to multiply here. And we're going to write it right there. But then we're going to add. That's the key difference here. We're going to add these two things to get our next term. Back to multiply. So we're going to multiply negative 16 and negative 2. And then we're going to add. Okay, that's the key, is you're adding, not subtracting. Now I'm going to multiply again. And then I'm going to add these two things. Now we need to put the variables back in. So it asked if this is a factor. We took a cubic. We took out a linear. So this cubic is now a quadratic. And this last number here, that's our remainder. Okay, I'll say that again. We go from a cubic down to a quadratic, and the last number that's sitting here, that's our remainder. So that tells me that, no, this is not a factor because my remainder was not 0. Now, they'll still give you problems that look like this. We're just going to focus on the coefficients, and we're going to do the synthetic process. Now, I put this one in here because, again, there's a missing term. There's a squared missing. We're going to put it in. So the first coefficient is 1. The squared term is missing. There's the linear term. And there's my constant. And since we're dividing by x minus 7, what goes in the little box here is actually a positive 7. So I'm going to be multiplying by 7. Bring the first term down, multiply, add, multiply, add, multiply, and add. That last term is your remainder. So this is a good sign. That tells me that I can divide these two things. I started with a cubic. Now I'm going to be down to a quadratic. So I put my variables back in. So when I take this cubic divided by that linear, I get x squared plus 7x minus 8, and no remainder. That tells me x minus 7 is a factor, and this is the other factor. Let's take a look at one more. Little box, coefficients, and notice I took the signs with them. Okay, it's not just the numbers, it's the numbers and the sign. Multiply and add, multiply and add, multiply and add. This one also worked. Put my variables back in. We were at a cubic. Now we're at a quadratic. So I found out that that is a factor. Now here's the catch with synthetic. You may be thinking, well, why don't we just use synthetic all the time? You'll notice that everything I divided by in every one of these problems was linear. There was no x squared plus 1 or x cubed minus x squared. Everything I divided by is linear. Synthetic division only works when you're dividing by something that's linear. Okay, so that's one of the downfalls of it, but it is great to use when you have that linear factor. The last theorem I have up here kind of ties this all together and adds one more wrinkle to what we've been talking about. It says if you divide a polynomial, which we've been doing, with a degree bigger than 1, every one of them has been, and we divide by x minus a, that's what we've been doing for the most part, then the remainder is p of a. So I've got an example here. I'm just going to start by dividing it first. So we're going to find out what p of 3 is. So we're going to put our 3 in here, and we're going to pull out our coefficients, 1, 0, negative 2, negative 1, 0, and 2. Okay, I put my placeholders in. I'm going to go through my synthetic process. But now I'm only really concerned about the remainder. If you would take 3 and plug it in here, here, and here, you would get 182. The same thing I got by doing synthetic division and getting my remainder. So let me back up. If I plug a 1 into this function, I'm going to get 0. And if I plug a 7 into this function, I will get a 0. If I plug a negative 2 into this function, I'm going to get negative 220. So that remainder theorem ties together what we've been finding with our synthetic division and what we get by plugging a number back into the polynomial.